Hello and welcome back. Today we are covering lesson 84 and learning about identifying quadratic functions. So before we get into quadratic functions, let's briefly remember what is a function. So you can look back at lessons 25 and 30 for some basic information about functions. But remember, we use function notation, which oftentimes looks like this: f with an x in parentheses or some other letter. Sometimes we use g or h or really any letter can be used as part of function notation, but most often we use f. And remember that we read this as f of x. And that is set equal to some expression. And remember that the x, or whatever variable is inside the parentheses, is the independent variable. And that is the variable that is the input to the function, or it's part of the domain. So there's a lot of information that is contained inside that x. The x's are the inputs to the function. They're independent. They just get to be whatever they want to be. And that group of numbers, which oftentimes is all real numbers, that are the inputs, the independent inputs to the function, are what we call the domain. And then let me just erase these words here. The function itself is the expression. And the values for the whole function, not just the x, but the whole function, which we could also say is the expression. This is the dependent, or the output, or we call that group of numbers that are the outputs, we call them the range. So the dependent variable is what comes as a result of the independent variable, and that's why we call it a dependent variable, right? Because it depends on the value from the domain. You can also think of it as the output of the function, and that group of numbers that represent all the possible outputs that come from all the possible inputs is the range. So nothing new here. This is exactly what we've talked about before. I just wanted to refresh your memory. And although we oftentimes use function notation because it can be really convenient for some situations, remember that the function notation is also equal to the y. So sometimes we use y and sometimes we use the function notation, but they are the same. They are equal. And we use y when we're graphing because it's a little bit easier to just say one letter instead of a whole expression. And we use the function notation oftentimes when we are using the function with other functions or doing something else to it. So many of the functions that we have looked at in this class have been trinomials, which have 3 terms. And many of them have actually been quadratics. And we have a standard form that we are already familiar with. So again, just to remind you what that looks like, it looks like the function f of x is equal to a times x squared plus b times x plus c, where a is never equal to 0. And what we have here is we have the coefficient for the x squared term, the coefficient for the x term, and the coefficient, or just the constant term itself. And recall that when the highest degree term is squared, that's what makes it a quadratic. So if we didn't have the squared term here, and we just had a first degree term, then this would be a linear function. And if we didn't even have that, if we only had the constant, it would just be a constant function. But we do, in this case, for the purposes of this lesson, we're looking at terms that do have that x squared terms, which makes it a quadratic. So remember, this is our standard form. We have the x squared term first, then the x term, and then the constant term. So just as a reminder for polynomials in general, a linear polynomial, most oftentimes we put it in the form of y equals mx plus b. This is a first degree polynomial and its graph is a line. Now we just finished having a discussion about quadratic functions, and their standard form is in decreasing order of degree, so ax squared plus bx plus c. This is a second degree polynomial, and its graph is what's called a parabola. And if you're not already familiar with parabolas, we are going to be talking about them much more in depth. And just as a note, a cubic function, we're not really going to get into detail in cubic functions at this time, but as you can imagine, it has a cubed term as its first term, followed by an x squared term, followed by an x term, followed by a constant, and this is a third degree polynomial. So to start out with, we need to be able to quickly identify if a function is quadratic. If we want to do other things with quadratic functions, which we do, we need to be able to identify them first and foremost. So let's look at at a function and say, is this a quadratic? And this is what we're given. Y minus 2x is equal to 3x squared plus 4x. Now you might say, oh, yep, there's an x squared term, I'm good to go. But we always need to simplify first and put it into standard form. So I'm going to make a note that says standard form is required to check, because sometimes, as you know, when we simplify equations and manipulate them, sometimes we end up eliminating terms and as we're simplifying, and we end up with something that is not exactly what we thought we would have. So let's go ahead and put this into standard form so that we can be for sure that it's a quadratic. So in order for it to be a quadratic, we want it to be equal to, for y, to be equal to that ax squared plus bx plus c. So we need to have the x squared term plus the x term plus the constant. So the y right now also has this 2x term. So I need to add this to both sides. And I have 3x squared plus 6x. And so this is my standard form, and you might be saying, is it really in standard form? Yes, it is. The constant is just 0. So remember, in our standard form, the constant can be 0, the x term coefficient can be 0. It's just this x squared term coefficient that cannot be 0. So it is a quadratic. So the answer to the question is yes, it is a quadratic. Now we can graph quadratic functions, and we will get much more in depth with graphing them in a future lesson. But for now, we can graph them with a table. We can graph anything with a table, right? So let's say that we want to graph this function. We want to graph f of x is equal to x squared. So remember, when we're making a table, in order to make a good table, we need to have some positive values and some negative values. So I'm going to put -3, -2, -1, 0, 1, 2, and 3. So -3 squared is positive 9, -2 squared is positive 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So then I can graph this, and rather than graphing it on graph paper, I'm just going to sketch out my axes and make sure I put enough tick marks on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I have -3 and 9. So that is about right there for that point. -2 and 4, so that's about right here. 1 and, or negative 1 and positive 1, 0 and 0, 1 and 1, 2 and 4, and 3 and 9 again. So then I draw a curve through all of these points, and it's going to continue in both of these directions. So I draw my arrows, and there is my graph. And this shape is a parabola. So remember I mentioned earlier, the quadratics have the shape of a parabola, and this sort of U shape where the U is expanding out in both directions is the shape of a parabola. And the parabola can be oriented all different ways on the graph. It can be narrow, it can be really wide, but it still has that general sort of expanding U shape, and that is a parabola. And we will go much more into depth for parabolas, but for now, let's just notice one thing. So this parabola that I drew here in red, notice that it opens upwards. So the U shape is opening up. I could also have a parabola that is a U shape that is expanding, but it opens in a downward direction. And the part of a quadratic that tells you whether that is opening up or if it's opening down is the coefficient on the x squared term. So I'm actually going to erase some of this so that we can take a look at, again, the general form, the standard form of the quadratic function. So a times x squared plus b times x plus c. If a, this a here, if it's greater than 0, it's positive, in other words. If it's a positive number, it opens up. So we don't even have to make a table. We can just look at this number and see if it opens up or opens down. If this number is negative, it opens down. So that kind of corresponds to the pictures that I already had drawn here. So looking at this equation or function that we just graphed, we see that a is equal to positive 1. So we have a positive 1 coefficient here, so it's positive. So it opens up, and that's exactly how our graph turned out when we graphed it with a table. But now we can just look at it and know, without having to make a table, whether that parabola opens up or it opens down. So for example, we can look at another equation. F of x is equal to x squared minus 3. Now this is already in standard form because it's in descending order of degree. And all I need to do is look at the coefficient here, which is positive 1, so it opens up. And I can look at another one. F of x is equal to 3x minus 4x squared plus 1. And I have to be careful because this is not given to me in standard form. This is given to me in just some rearranged form. So I need to put it into standard form. Negative 4x squared plus 3x plus 1. So now that I've taken care of that, I can look at my x squared coefficient. It's negative 4. So this parabola would open down. So I didn't have to make a table, I didn't have to graph it, I could just look and see which direction these parabolas would open if I did graph them. And that's it for this lesson, and I'll see you next time.